Good evening, Tuesday night, May 2023. Well, imagine that this is a talk about analysis and methods again, analysis and methods. And over the past many talks now, these talks are adding up. So we kind of have some talks that started with like Serlo and a dictionary of symbols. We have Leonardo on art, Leonardo on painting. So we have some of the philosophy of art. Some of that comes from home, and then a lot's been going on with the deconstructive analysis, and there's some more coming about the deconstructive analysis and the postmodern and the theory of knowledge in the postmodern. What is even the postmodern? Well, the postmodern is kind of since the modern, ante and post, pre and post, ante and post, that the postmodern is since the modern in a sense. Does that in terms of information technology and theory and this advent of the internet. I found this great book about the postmodern that'll kind of advise some more what goes on into the deconstructive, that's part of the entire literary field of that kind of thing. But then for something like Descartes, once upon a time, Descartes was modern and postmodern, and now he's what we call canon. And it's a very particular thing. This readings from Einstein's Out of My Later Years have been very fruitful. Out of My Later Years was just, for me, it really helped me understand a lot better what the very few and basic rules of special and general relativity are, what Einstein's instincts and intuitions are leading him to develop, why it's going into helping explain what goes on in the macroscopic and in the structural chemistry, the molecular chemistry. So that we've had some readings about philosophy and into the deconstructive and theories of reasoning and all this kind of stuff. And then there was analysis, and it started with, for example, standard analysis, which is calculus. The integral calculus is familiar to anybody who's ever had delta epsilonics and ended up having integrals and then being able to work with the integrals, and not necessarily with the usage of the differential as a raw quantity, which is then negligible wherever it's left over, which is kind of methods of Leibniz and this kind of thing with regards and with respect to what comes and goes from those things that we've read quite a bit out of these books here, and so these are the ones we kind of haven't got to. But then after that there was the non-standard analysis. So what's the non-standard analysis? Well, for some, it's more retro-classical, paleo-classical. Aristotle's continuum is this. Line points in a line, the iota values, the range of the equivalency function, the natural unit equivalency function, a countable continuous domain, not a real function, not a Cartesian function, but in the realm of theory, so primary, central, and fundamental, as a definition of continuity, that it's retro and paleoclassical, but then again, once it's possible to bring it forward into the modern and postmodern, it really becomes a thing. And so then there was just some more discussions of this analysis and methods, which it's largely been about the differential. So with this idea of the sheaves, which are topologies, and submersions, which are differential geometries and linearizations, and the symmetries, which are central in systems, lots of systems of differential equations. Then there's been several talks about the differential and with regards to the exponential, and that a function is its own antiderivative in the operator calculus up above them. So already we have theories of sets and parts, integers and real numbers, the objects of geometry, and basically that's usually enough just kind of reversed and back in that order, or geometry, integers, real numbers, sets and parts is fundamental. Then functions are basically these mappings, these relations are first class in the theory of functions. That topology is much similar to function theory, except it really just defines the relations of neighbors in a spaces. So topology is very much geometries, and the abstract of geometries, abstract geometries being topology. And then there's something like category theory. Then there's type theory, of course. Type theory is a very usual milieu for, especially in the patterns of language, like programming language and type inference and this kind of thing. As someone whose usual role is reading source code of program languages and determining where to put in a fix and knowing the correct syntax to make such a thing. Being a programmer or software engineer. Type theory is one of the greatest boons to programming because it allows tools to, in the sense of the types being sensible, fungible, and tractable, to extract relations in types and to establish relations in types and to enforce relations in types that make it possible so that the relations and types hold up safety and what are called guarantees. In programming, we like to have guarantees. And it's the same thing with mathematics and proof. What results is from guarantees are these things which allow us to then know what's well-defined behavior, defined behavior, and what is undefined behavior. And so as we get into that, then what we have is a lot going on are these things. So looking around a bit, this is a good little book I found some time ago, 200 Puzzling Physics Problems with Hints and Solutions, and it's from Cambridge University Press, and it's just a very useful thing to cover lots of different examples of problems in physics, and I'll be looking at that here in a while as I get into that. And then there's this thermal induced gas phase reaction, so this will go here. That I'm kind of just organizing the books, and so some of what we've read, like we've read most of Mogan's nonlinear electromechanical effects and applications, and it's a serious course, and it involves lots of different methods of analysis and techniques. Goes into its own kind of thing. And then what I have here, this is only a subset of my library, but what it is a bunch of things that have kind of come together. This, for example, was the 1950s or 60s course in mathematics, an honors course in mathematics for a year or two. Topology, functions of a complex variable, the vectors for linear algebra and also for real analysis, the Schwartz function and its applications. Now that gets into a series of numbers with very particular and well-known or particular and surprising facts of the relations that reflect that for something like Bernoulli numbers or Pascal's triangles, the binomial theorems, coefficients in numbers, Schwartz functions, different kinds of functions, that these have properties that then establish guarantees that then make it possible to have tables or means of the, tables, or how you have means of interpolation and the numerical methods and approximation to get out what are these things. So for example, this book, and it's from 1950 or so, 1960, published by the Mathematical Association of America, 1974, but a reprint maybe, the Schwartz function, geometrical interpretation of, page 29. And what it says is just an example to help, characterize in the catalog, that Z1 and Z2 be two distinct points. So it's any 2 points. Where do they live? They live on a plane. Because any 2 points define a line, and any line defines any number of planes, and two non-collinear lines define one plane. And so on. That then the author describes that the transformation TZ equals the absolute value of Z1 minus Z2 over Z1 minus Z2 times Z minus Z2. So the difference in terms of the point and these other 2 points by the length of their distance and the distance from first to second, resulting in a quantity. It doesn't say whether Z1 and Z2 are greater or less than each other. So it's to assume that then it's just going to have these mirrors and reflections as coordinate symmetry about magnitudes and their sign, their absolutes, is a rigid motion which brings z2 to the origin and z1 to the x-axis. So this is kind of like when we were talking about the abscissa, which is, well, what's the abscissa? It's if you have a function and you have a point on that function according to a vector, dropping it to the axis. Its inverse is t inverse z equals the quantity of the quantity z1 minus 2 over the absolute value of z1 minus z2 times z plus z2. So that looks like the parametric form for a line because in z, that's a line where the slope is z1 minus z2 over the absolute value of z1 minus z2, and the intercept is z2. Transformation rz equals z bar is a reflection in the x-axis. So it's defining in terms of these symmetries and that, where it is. Hence the composite function t inverse rt reflects z in the line L determined by z1 and z2. So this is a pretty remarkable fact. It establishes that according to the composition of these functions, where a function has a given type of its inputs and outputs. And so functions of like common types can be composed and it can be invoked or made algebraically. So a quantity, which results this function, it's a composition of these other functions. And so this notion of the adjoint and these other kinds of things from the tensorial analysis are so familiar from the linear algebra, where when you have the inverse and the adjoint, that it builds the Hermitian, and it builds the adjoint, and it builds the Hamiltonians, and all these kinds of things that start to become familiar, that this composite function reflects z in the line L determined by z1 and z2. And so this is really cool because it takes a function as defined by any of these 2 points on the line, and given another point, it reflects about it, about that. So it's as if to draw the line between z and this line is that otherwise you might first usually make a parametric form of the line and then compute the distance between z and that line at its nearest point, determine the minimum of those distances, and that point connecting z makes a line orthogonal to this line, and then opposite that on the other side, the same distance would be its reflecting z in the line L. And so that's cool that it says it is easily computed to be z star equals t inverse rt z equals z1 over z2 minus z2 quantity over z1 bar over z2 bar quantity times the quantity z bar minus z bar 2 plus quantity z2. So that's given that RZ is a reflection in the x-axis. So that just basically says whatever the x-coordinate is, negative x. So comparing this with 5.11 or 3.7, some earlier formulas, we see that z star equals the s sub z bar, where sz is a Schwartz function of L. See figure 6.1. Reflection over inversion of in a circle. So C of z minus z naught equals r. The definition is as follows. Let z not equal to z naught. Draw the half ray L plus from z naught through z. Locate the point z star on L plus such that z star minus z naught absolute value times z minus z naught absolute value equals r squared. We must therefore have z star minus z naught equals sigma z minus z naught sigma positive. Hence sigma of the quantity z minus z naught squared equals r squared, so that z star equals z naught plus quantity r squared z minus z naught over the absolute value of z minus z naught squared equals z naught plus r squared over z bar minus z bar naught. Comparing this with 5.12, we see again that z star equals S bar z, where sz is the Schwartz function of the circle. So we have Schwartz function of this line, and we have Schwartz function of this circle. So looking back a bit, that it helps define reflections. This can be very useful because you wonder, well, what's the curvature of a thing? Well, you draw a circle to it, and it's tangent in the region about that point, and then whatever is that radius is one definition of the curvature. And 1 over that is also one definition of the curvature, because, well, a straight line has zero curvature. And so only like the radius would be infinity, and so 1 over infinity is 0. And then that's getting into the definition of curvature. But another one is to say, whenever you have a curvature, you make a locus or whatever, and then so you have a complementary curve that takes like a hairpin in and out of it, but like just as close as possible, because it can kind of be to like 1 over x, but angled out, pointing out of that, and then that from that depth you can kind of determine a measure rate of curvature in a smaller kind of way. It's a different definition of curvature, kind of as about a 45-degree bend instead of a circle's constant curvature that takes a bend. Like what is that measure of curvature? These are different kinds of ways to get into what are quantities reflecting properties of these functions that normally we always deal with in terms of like the slope or of the parametric line. Y equals mx plus b. Rise over run is the slope equals m, as in that parametric form of the line. But then when you look at curvature, it's pretty much arbitrary how to find it sometimes, and only some very particular formulas have these curvatures of this form. And then otherwise we often deal with just the derivative, or the computing the gradient or the slope, or the derivative at the given point after you've given the derivative of a formula for this function, according to many rules available to computing the derivative, or estimating the derivative, approximating the derivative, given functions that estimate or approximate it. So this kinds of things then in terms of computing like these inversions and in geometry and about this by these arithmetic quantities just in sine over sine and taking products as about these reciprocals and stuff in algebra are pretty good. And so then we would look and see what a function is. This function, I'm looking for a definition, because this is an analytical tool that the curriculum of this day has stood up with deserving a book as much as linear analysis, ordinary differential equations, real numbers, complex functions, and these kinds of things. So we'll look at the function about the use of conjugate coordinates and the Schwartz reflection function. The path has been fared, as draftsmen say, to pass in a wide arc near a number of allied topics in complex variable theory. So conjugate coordinates are introduced, and then elementary notions of plane analytic geometry are expressed in terms of conjugate coordinates to establish the 9-point circle theorem and Feuerbach's theorem. And in chapter 5, the Schwartz function of analytic arc is defined and numerous examples are given. So let's see what this says here. That's where I've got from straight lines and circles, we turn to analytic arcs and curves. We suppose that the arc C is written in rectangular form, fxy equals 0. Conjugate coordinates, this becomes f of z plus z bar over 2, comma z minus z bar over 2I equals g of z bar equals 0. Oh, okay. So it's already in complex numbers, and so the plane is a complex plane, and then these are these points, and it's already making use of this arithmetic of these things, and you could almost make it so that you don't do or don't have to leave in or out some of these other things to do with complex numbers, because you don't even need all of arithmetic to make most of arithmetic. You can have this is one thing I wanted to get into a bit. So there's arithmetic, and people are familiar with the operations of arithmetic. There's addition and multiplication. There's subtraction, it's addition's inverse, and division, multiplication is inverse. And multiplication is higher order addition. and then it just so follows that everything else can kind of be built up and falls down from that. So you have fundamentally one operation and its inverse, and then the establishment of where there are even multiples or even divisors, that whether the operation of division is closed for inverses, and that it's so when it's possible to just have that the multiplication is only open and closed to or with respect to multiples instead of with sums. Now together it makes the field, and it's most familiar because that's how arithmetic works. It's so that the numbers add up this way and make their geometric products like squares, and they make their integral moduli like even numbers and tens or powers of 10, all these kinds of things. So another way to look at that is it's pretty clear that addition is fundamental, because the very act of counting is just increment, addition plus 1. So even just starting with addition plus 1, then addition of two numbers is a higher order increment. That then multiplication is kind of a higher order. It has a variadic number of arguments that establish what round of terms it would take to do it. It's of higher order. Compared to first order is that it's got one operand and one operator and one operand from the given accumulator, or the stack, or the starting point. We talk of functions being either unary or binary. They accept one argument, they accept two arguments. The variadic function, from the language of functions, accepts any variable number of arguments. An ellipsis, ... And so here, when you take the sum of two things, then it says a matter of taking all the increments that went into the one and all the increments to get together, and taking all those increments apiece, and then that results from 0, counting down, for example, to 0 for each one, and then counting up for however many one of those each counted down in that one. For example, it's implemented by a stack, or implemented by a counter, or implemented by pebbles on a beach, or an abacus, or any of these other different machines. So as you can see already, it's one thing to define arithmetic as these are the operations and they're closed. And it's another one to define these pieces or fragments of this overall arithmetic. We're going to call it, elementary arithmetic of the ordered field, or the rational numbers, and that the results that you can get a lot of the facility and strength of these things in just subsets, as it were, of these operations on the arithmetic and the numbers. For example, restricting only to the positive numbers solves a lot of problems. They're signless magnitudes. Now, for some people, those are the only numbers. They deal in a world of magnitudes. In some people's worlds, they deal with only differences. And whether these differences are signed or unsigned also reflects that they're magnitudes, that the difference of two numbers is, for some, that's the first, what is the first order of arithmetic? Is it addition or subtraction? Or is it multiplication or it's division? And so there's lots of ways, and not just one, to arrive at what abstract algebra later in the development of the linear curriculum of the standard analysis has the ordered field to make the complete ordered field by algebra of arithmetic from a field being a group. A group is just an operation on a set of elements that's closed and it has an inverse. So whereas like a semi-group is sort of like an operation on a field of elements and it's got no inverse. So, and these are names for algebras, and then you can treat these algebras abstractly, like I have a theorem that applies to any group, or applies to any field, or ... Whereas then these other parts of algebras, and basically anything that's an abstract form of objects of say arithmetic, or an operator, really, or functions for function theory, makes for an algebra, which is also kind of where we get, that's named for a guy named Algebra, who is a part of when it was in the Dark Ages in Europe. It was like in a really Enlightenment period in the Middle East, or Arabia and Mesopotamia and Persia and this kind of. So at that point in time, the scientific center of the world was today kind of still where we get the Arabic numbers, which came from the Indic numbers in a sense. The Arabics having added 0 or something. That so algebra is named for algebras. Long before a Frenchman named Galois came up with group theory, which then became just a standard part of the apparatus of the standard linear curriculum. All sorts manners of developments were already called algebra. And it reflects the key thing about algebra is it reflects symbolic and abstract quantities instead of numbers and rules for computations on them. X and Y, the usual names for variable is X, usual name for variable, and the usual name for an integer variable, and A, B, and C being the usual names for geometries variables. So coming up forward then about the arithmetic, then if addition is kind of first, and it's because it's fundamental, and then some might have, well, subtraction maybe would be first, but really addition is first and subtraction is inverse. And then there's that, well, is it closed or is it just bounded by 0 below? You can have it either way. One of them is a model of the non-negative or positive numbers, and the other one's the model of the positive or negative integers. And that all ends up filling up the number line. The number line is the same as all the real valued space. And then there's the long line, which is like, yeah, if you have to extend that, then if there's a point at infinity. If you have to extend that, it's the long line. And if you have to get any more refined than the real numbers, it's like you can't because it's a continuum of them. So whatever lives as infinitesimals in the real numbers in the real number space is about like 0 or what. But anyways, that's a long ways down the development. But starting with the addition of the integers, then another way to look at that is instead of that, then that has higher order operations making multiplication, which it does. You can always just still build those again. But the idea is here that for these fundamental and elementary operations, and I kind of thinking about this for a while, is that you want it to kind of be, on one hand, first order, meaning that the operation carries forward in first order. And all its products, any given pairwise product is first order. And then whether it's infinitary. What does that mean? Infinitary? That means whether it goes to infinity or not. And so it's like, well, what's the sum of all, what's like the result of incrementing all the many times? Well, it's infinity. Is it open or closed? Otherwise to that, say, well, yeah, it's closed. It's closed because any result of applying the operation is still in there. And so then it's like, well, is it open or closed? If it's infinitary, it's like, well, yeah, it's either open or closed. So anyways, then the other idea is then instead of having a higher order operation for multiplication, the integers, is how to make it so that division is kind of the next thing. Because what's division? It's like, how do you count things? It's like, well, I have an increment and I make increments and then I compare it to things. And then, well, what's this opposite? Is well, I have division. I can make a split, or a division, and then it results that if I make a division, then whether it's first or second order division to split it just once a piece, or whether to split a given number of pieces each. And then as well, whether you can make even cuts more than one, or if there's only one way to make a cut and it's even. So the idea is that it's kind of like when you have sets as the primary elements and then you implement the model ordinals for integers in them to make addition, and then higher order addition is multiplication, or Peano and Pressburger arithmetics. Okay. Or, which is where Pressburger arithmetic is kind of like Peano arithmetic, and it's got addition and multiplication's higher order addition, except Pressburger has a schema, just like one of ZF set theory's axioms is a schema to keep it from being arbitrarily high order in terms of that everything should be first order in terms of the number of predicates, so the number of variables that it takes to express it in symbolic form. That another way to think of this is how it's possible to say, well, we have division and it's first order on the other side, and infinitary that results that the idea is to start with arithmetic with addition as increment and be in first order and infinitary, So it ranges from 0 to infinity, and it's all the integers that way. And then there's division, and it's first order, and it's infinitary to start with 0 or 1, or start with a single magnitude, and then just divide that into halves, and whether that goes into thirds then, or whether that goes into powers of 2, is different ways you can imagine how you can define division when it's not after the integral moduli, any type of way to break it down in terms of the integral moduli or divide something, or as after the integral moduli and the longer division, or this and that, when there's terms left over in the additive or overflow or carry. That this is a way to look at then these two operations, one of which basically counts from 0 to infinity, and the other one which basically analyzes or divides from 0 to 1 down to infinitesimals or 0. And then how that can be well behaved and well defined is to make it so that, well, elements like infinity and dividing by 0, or dividing to 0, have that it's adding to infinity and dividing to 0. These are kinds of examples of that. Then when we say, well, we're not even going to have to worry about going all the way to infinity. We're just going to go to 4. And so then we might add up to 4. And then when we start with division, we might just start in a division of 4. And then how soon we can get from that to the same thing as if we were just adding 2 plus 2 or multiplying 2 plus 2 and getting a 4. That the bounds basically reflect then the way to take a look at what's the effectively infinite and how these finite models of the things add up to the full analytical real valued systems of numbers. So, I have studied, say, foundations in set theory and number theory, got a mathematics degree, abstract algebra, computer science, computer numbers, machine integers, unsigned integers, magnitudes, floating point arithmetic, fixed point arithmetic, many kinds of numerical representations. The continued fractions are another way to write numbers. The numbers can be written in any radix or base, or usually decimal, and the decimal point is called the radix. And there are numbers, from 0 to infinity that are non-negative. So anyways, as I've been thinking about this and trying to figure out how to define, arithmetic, it kind of ends up being in these terms, addition and division. Because then for the sets modeling these ordinals for arithmetic, then the parts, they're making boundaries in wholes or part theory. It's kind of a complementary dual of set theory, part theory, is for the objects of this division, and then the other one for the objects of arithmetic. Then for having all their finite models, finite bounds, kind of attain to them, make it different from that like, well, how's addition over there? It's like, well, it's got a lower bound and no upper bound. It's like, well, we only have an upper bound. We only have finite resources. It's like, well, it's out. You can no longer use it for that. You'll have to use a finite ring. You'll have to use some other means to define what kind of algebra operates on it and what its algebraic properties are to result quantities in it that are numbers. And then it's similar with this division. Well, what do you mean it's unbounded and effectively infinite? Well, it's just a very, very large number, and it ends up being smaller, and you'll have to use interval arithmetic to compare these quantities you get out of it to keep them sensible so they're fungible and tractable, and it's called floating point arithmetic. All right? And so these are the kinds of things that get into and out of these usual means of representations of models and numbers that for everybody, everywhere, is available as arithmetic with addition and multiplication and their inverses, subtraction and division, till you get to increment by infinity or division by 0. That then they build up what are the roots, because numbers have powers and roots. So this is kind of like, what are the powers of the increment? They're sums. What's the addition formula for this taking the increment to or the successor function, the increment, to this next one? Well, it's got an addition formula. They just add the values as a result of increments, and it's the same as if you took the increment of each of them. All right, and for multiplication, yeah, it's about the same. Oh, what then what happens? Well, you can get up to tetration. The tetration is an example of an addition formula that results, but first there's exponents for these powers. You can just take the sum of two powers and sum their, or take the product of two powers, excuse me, and sum their exponents, and you can compute the product of two powers as via an exponent. Well, that's great, powers and roots, all right. Well, what happens when you get out to infinity? It's like, well, it's kind of undecided. There's a model either way. There's one model where the point in infinity is prime, and another one that it's composite. There's a model where the point in infinity is a power of 2. There's another one where it's not. There's one where the point in infinity is a power of 2. There's another one where where it's even, say, or that it's even. That it's a composite and that it's even. And there's another one where it's on either side of it are even numbers. There's a model where there's an infinity, there's a point in infinity, and whether or not it's surrounded by twin primes or triple primes or not. These are things that get into then where you can be able to separate what are the models of the bounded and unbounded from arithmetic, or the closure and unclosure, the algebras, for these groups and for these concepts and products and things in algebra, that result then being able to take as a limit of those the emergent values that are the integers. That the integers are whole because they're put together from all these different things. Besides is that they're usually also our clear interface. The integer valued part of the real number is the first measure of its magnitude. Surely the most significant part. The idea then is that these applications for analysis of these numbers models, they can help make it so all kinds of things that result, approximations and numerical methods besides, also helping consider what happens for these analytical methods, where it's basically it's like, well, does a root exist, or can we apply methods that make an even multiple and even divisor and ... Or does analysis make it fair, that it's balanced, that it works out, that it can be even and spread out, that adds back up as if it were computed? These are some of the kinds of things that go into foundations of arithmetic. So getting way back to this function, it's a function that implements some reflection formula about lines, so that if you have a line and a point off the line, that you can compute it, this point opposite it, and it seems to be built upon with this Feuerbach's theorem, what's called 9-point circle. The clinant of the side Z2, Z3 is defined as various inverses and reciprocals of conjugates, taking advantage of the fact that these products of conjugates implement these things. This gets into basically then for why it's most useful that everybody's going to already be dealing with arithmetic anyways, and they're going to be real valued variables. Well, we can't really restrict people to a particular subset of the numbers that have these properties. Well, make it a superset instead and let them be at their own risk out in the complex numbers, instead of kind of at a loss how to extend these simpler closed subalgebras of the real value numbers. That's a kind of usual thing, and it's standard, that after these elementary geometric facts built upon the complex numbers, that these are some kinds of things that get into what result analytical methods for the use of formulary. Center of gravity T, the intersection of the medians. This is a description of the 9-point circle. The 9-point circle. And what it is diagrammed as like to so, with a figure 4.1, the 9-point circle, as having a circle, and it's drawn a triangle that then will be described by so. Given a triangle T1, the 3 midpoints of the 3 sides, the 3 feet of the altitudes from each vertex to the opposite side, so these would be like the abscissae, and the altitudes from each vertex to the opposite side, So for any given triangle, the three midpoints define a circle. What define the points of the circle are the right angles that connect the opposite vertex. So it's got a triangle, and then at each vertex is drawn a line to the opposite side that is orthogonal or perpendicular to the opposite side. And the circle there's a point on the circle for each one of those. So the circle is both inside and outside the triangle, mostly inside the triangle, of course, but only some of its arcs or chords are outside the triangle, where it's so that opposite what would be a less than 60-degree angle is where it would be opposite where it's less than 60-degree angle is where it would be inside, and otherwise outside. Given a triangle T, the three midpoints of the three sides, the 3 feet of the altitudes from each vertex to the opposite side. So those are the altitudes, these things. And the 3 midpoints between the orthocenter, i.e. the intersection of the altitudes, and the vertices all lie in a circle. So it's those in the midpoints of the sides. That's kind of interesting. So it's saying that this is always going to define a circle, this triangle's altitudes and the midpoints. Those points define a circle. The radius of the circle is half that of the circle circumscribing T. And he declares that I've never seen this proved, the radius of the circle is half that of the circle circumscribing or outlining T and touching each its vertices and so on. The center of the 9-point circle lies halfway between the circumcenter and the orthocenter. That the circumcenter and the orthocenter are connected, and that the center of the circle is also halfway between it. This is the theorem of the 9-point circle. Now, I've heard of casting out nines, but I've never heard this 9-point circle theorem before. And I'm thinking of some, I wonder if it has to be applied that there's some like very obtuse triangles this would not apply. I don't quite know. In proving this theorem, it is advantageous to select the circumcircle at the unit circle z bar, z times its conjugate, complexly equals 1. So this is another parametric form for a circle, kind of like x squared plus y squared equals 1. This is the way. Or quantity x minus y, quantity squared equals 1. Various parametric forms for the circle. Let therefore the vertices of T be z1, z2, z3, and note that z bar I equals zi inverse. For convenience, set S equals z1 plus z2 plus z3 t equals z1 z2 plus z2 z3 plus z3 z1. P equals z1 z2 z3. Center of gravity of T, the intersection of the medians, is at z equals 1/3 quantity z1 plus z2 plus z3 equals 1/3 s. The clinant of the side z2 z3 in brackets is this formula that equals -1 over z2 z3. Hence the equation of the side is by z bar equals -1 over z2 z3 times quantity z minus z2 plus z bar 2, or z bar equals -1 over z2 z3 is z minus z2 plus 1 over z2. So now I'd like to write these in terms of probably either some formulas about coordinates about the triangle or about the circle in terms of those, or otherwise about that the additive identity of the circle, and it's, let's just take the unit circle because that way we can use our multiplicative identity, and work identity is about algebra because 1 as a quantity is the multiplicative identity, and so it can come and go, and that's how we're performing this to leave these out bracketed in higher order equations until later it's only brought down so it leaves a parametric on the outside with the outer products that may be. I've not really seen this before, but I'm quite interested in it at the moment. Z bar equals 1 over Z2, Z3, Z minus Z1 plus Z1 bar, or Z bar equals 1 over Z2, Z3 times quantity Z minus Z1 plus 1 over Z1. Solving 4.3 and 4.4 simultaneously, which is a system of two equations, right? We find that the foot of the altitude is located at the point Z equals 1/2 times the quantity Z1 plus Z2 plus Z3 minus Z2, Z3 over Z1 equals 1/2 S minus P over Z1 squared. Two of the altitudes have equations. Z bar equals 1 over Z2, Z3 times quantity Z minus Z1 plus 1 over Z1. Z bar equals 1 over Z3, Z1 times quantity Z minus Z2 plus 1 over Z2. According to these ordering of the coordinates and the way that complex arithmetic carries it out, we could talk about how this goes in the higher order complex numbers and otherwise anything that algebraically leaves it up so that these various transforms and reflections and this and that provide for these operations the identities they need. Anything that does so will be so proven by the same proof. Solving simultaneously, we obtain their intersection. Z equals Z1 plus Z2 plus Z3 equals S. This is the location of the orthocenter. And where the center of the 9-point circle lies halfway between the circumcenter and the orthocenter. Note that the circumcenter is Z equals 0, the center of gravity, intersection of the medians is Z equals S over 3, and the orthocenter is Z equals S. Therefore, the center of gravity lies 1/2 of the way from the circumcenter to the orthocenter. The center of gravity, or the centroid, is quite a thing. It kind of expresses the maximum from any edge. And so it's pretty complicated and contrived because it also represents this it has various pathological forms which kind of add up for it, which make it hard to compute. The centroid, it's kind of like the locus, and the way those things are kind of framed. And I wish I knew them better because now I'm learning them. Therefore, the center of gravity lies ... The line joining these 3 points is called the Euler line, or Euler line of T. Its clinate is S bar minus 0 bar over S minus 0 bar, and S bar over S, and its equation is Z bar equals S bar over SZ, which can be written in the neat form. Imaginary part of the quantity S Z bar equals 0. That's defining a parametric formula for Z bar and S is solved together. The real number, imaginary SZ equals the matrix of the real Z, MZ, real S, MS, is known as the exterior product of the complex numbers Z and S, and is designated by Z star S. So we might think about the difference between dot and star with respect to these things. Usually the scalar product and this exterior product. We've been talking about the inner and outer products and the differential. And the inner products are usually with regards to that the inner product of two objects otherwise of the same type is some value of less dimensions than that, a lower order, and the exterior product is somehow of some higher order. But when you take the real part of it, then something like the cross product has, for example, that, well, yeah, it's still a vector, but it's kind of as vectors have taken a rotation, and so it's kind of a higher order, but then that part's discarded. Similarly, this real number here, known as the exterior product of these two complex numbers, I haven't really seen that defined before and left in that way. But it's just usually the absolute value of the matrix product of these things, where the imaginary part of SZ equals this. So that's kind of what's left in and out of here is this imaginary part of SZ that S is Z1 plus Z2 plus Z3, and Z bar is about the unit circle that Z bar equals 1. So this is a pretty interesting little thing about that when this parametric form for SZ bar equals 0 is satisfied, that the real number that satisfies, instead of that being equal to 0 is a thing, that being equal to the real part of Z and S is called the exterior product of the complex numbers Z and S, and is designated by Z star S. I have not heard of that before, so I'm glad I have this book and I've just read this. And about the 9-point circle, I imagine I can find much more. And so I'm going to be looking at it and see how much dust this has gathered, or whether this is one of these usual fundamental things that drives all sorts of manners of things and deserves analysis, because it can be taken apart and put back together in different ways. So then it gets into some geometry and finding some things, and the center therefore lies in the Euler line, halfway between the circum and orthocenters. It is now triviality to verify that the 9 points in 4.9 satisfy 4.10. Okay, I haven't done geometry in a long time, so this amuses me. Thus, the coordinates of the vertices of the tangential triangle are ... The midpoint sides the sides of triangle are computed to be ... Note that, furthermore, ... The equation and conjugate coordinates of the circle passing through Z sub I star, the 9-point circle of triangle, is formulas in the square of the differences of products, those being differences from these coordinates, equals a formula or an expression in the square over the square of this difference in of a product in the difference. That these have geometric attachments to them, but they're written algebraically and arithmetically in this arithmetic of these complex numbers. Solving that with Z bar equals 1, or this unit circle, we obtain S squared Z squared minus 2 STZ plus T squared equals 0. If we assume that the triangle Z1, Z2, Z3 is not equilateral, then S is not equal to 0. Alright, Z1 plus Z2 plus Z3. Since the discriminant of 4.13 is 4S squared T squared minus 4S squared T squared equals 0, it's a matrix, it's a product or a property of the matrix, it's some inner product of sorts. It follows that ... has a double root at Z equals T over S. Since the discriminant is 0, it has a double root. This implies that the 9-point circle of triangle is tangent to the unit circle at this point. If S equals 0, the two circles coincide. We can now wrap up this discussion in the following way. Given any triangle, there are 4 circles that are simultaneously tangent to the 3 sides. Given any triangle, there are 4 circles that are simultaneously tangent to the 3 sides. 1 circle is inside the triangle, this is the inscribed circle. 3 are exterior to the triangle, these are the escribed circles. That's, for example, the one that's from the diagram, this inside and outside. The 9-point circle of any non-equilateral triangle is tangent to the inscribed and to the escribed circles. This 9-point circle. This is Feuerbach's theorem. For the equilateral triangle, the 9-point circle of source coincides with the inscribed circle and is tangent to all the escribed circles. So this is pretty cool about triangles, and I was trying to understand that with regards to the Yenri, and it helped me understand. I'm not familiar with the word escribed. I knew circumscribed and inscribed, but this escribed is it's kind of as from the sphere packing. It's like, how many circles can you fit in a sphere, in a triangle? Well, you can inscribe a circle in a triangle, and then in each corner you can inscribe a circle in that triangle. These are these escribed ones when it's an equilateral triangle, because otherwise these escribed ones that are of the 9, you can either do the 9-point in the corner and in the corners will be equilateral again, or they won't because it's not equilateral. And then where they're not, then it's the 9-point circle again. If one adds to the 9 points already distinguished the 4 points of tangency just described, one might speak of the 13-point circle. Some authorities say there are 31 and some say there are 43 points of significance on the 9-point circle. One can again go on in this vein, multiplying miracles and proving many other theorems of triangle and circle geometry. However, we have other fish to fry. The other day, there's some memories. Now I'm really happy that I've just learned these kind of facts about some approaches to inscribing circles and triangles, packing circles and triangles, and inscribing and recursively inscribing in what's left over the circles and the triangles. And with regards to the circle being a special shape because it's round and its curvature is constant, and the triangle being a special shape because it only adds up to pi radians, not 2 pi radians, it's interior angles of a convex polygon. That then, about fish to fry, I was just reminded of being a little kid and we caught some trout or something like that, and it was at like in a outside environment, and it was like on a wood fire with like a big cast iron pan and some butter and frying some fresh fish. And at first I thought it would be terrible because it was, this fish that had been cleaned, and that was pretty disgusting. But after it was all fried up and then there was bones in the food. See, not all food is free of bones. You expect anywhere you go to a restaurant, unless they declare otherwise, or that it's in shells, they say, this food has bones in it, this fish has bones in it. So besides that, it's just one of the best flavors ever. Fresh fried fish in butter. So that's when he says we have other fish to fry. I'm looking forward to it. All right, so that's an interesting little factoid. You're looking at that. Look at that. This is a book on number theory, an elementary introduction. Greatest common divisor, least common multiple, fundamental theorem of arithmetic, Pythagorean triplets, those integers who form right triangles, the sides by their lengths, the sieve of Eratosthenes, the infinitude of primes, the prime number theorem. Take a look at the sieve of Eratosthenes. Oh, the sieve of Eratosthenes is to find prime numbers by striking out each even multiple of a number, and whatever's left after a given point that's under a given square of all these numbers by the last one done can be exhibited prime. But what I like about prime numbers is the quadratic sieve, where you draw a parabola, or y equals x squared, and you mark each of the integer points on the function. So an integer point is point. It's an integer in x, an integer in y. So 1 and 1, and 2 and 4, and 3 and 9, and dot x squared. So then there's the left branch and the right branch of this parabola, because there's negative 1 and 1, there's negative 2 and 4, negative 3 and 9, and all those integer points, So you connect all those integer points. Every single one has a line connecting them. And so each one of those lines from one branch to the other branch crosses the y-axis. And so, for example, between 1 and 1 and negative 1, 1, it crosses the parabola at 1. Between 2, 4, and 2, 4, it crosses the parabola at 4. And so 1 is not a prime number, 4 is not a prime number. Nothing crosses at 2, nothing crosses at 3. Those are prime numbers. So anyways, as it gets higher and higher and higher, and you all the lines are connected, and you ignore the lines that cross that is not an integer point yet, but still they have significance. But wherever these integer points of the parabola connected cross the axis, and it's at an integer point on the axis, it's a composite number. And wherever it doesn't intersect an integer point, it's a prime number. This is called the quadratic sieve. And it's one of the most interesting things I don't know much about. And it's hard to find references in relation to it. You figure it would be like this is boggling. It relates squared and prime numbers. There's many things about prime numbers, like the prime number theorem is that how many numbers are prime? Well, approximately log x. So you mean that approximately of these numbers, approximately the logarithm of the unbounded or the maximum of them are prime, and then it's connected to x squared, and it also defines the fundamental theorem of arithmetic. Yeah, that's not something. The fundamental theorem of arithmetic is composition by prime factors. Each integer has a unique prime composition, prime factorization. Oh, and then we'll get into congruences and modulo. It's the usual operation of the leftover carry or remainder after overflow, and this kind of thing is the modulus. About the modular and the modulus. Residues, I've forgotten what residues are. I've forgotten what congruences are in the numerical. I've forgotten what congruences are, except that in geometry that means they're alike. And it is pretty much reflects the same in number 3 or 2, that they're not incongruent. Finding integral solutions of conditional congruences where fx is a polynomial with integral coefficients. So if we say that a congruence has r solutions or r incongruent solutions, we shall mean that precisely r of the numbers in any complete residue system modulo m are solutions of the congruence. All right. CRT, Chinese remainder theorem. There's lots of different ways to compute division and compute trial division and test numbers for divisibility by other numbers. I call this digit summation congruence. I figured out a way that made it possible and pretty simple to have for machine integers to, like casting out nines is, well, if you can add up the digits and it adds up to a multiple of 9, and you can do that again and again until you're down to something that you can definitely tell is a multiple of 9 or not, then the thing is a multiple of 9. And it's similar with 3. And why it is it's so for b squared minus 1 and any of its roots. So 9 is 10 minus 1. And so in other bases, like in base 27, you can compute 6 by adding it up and seeing if what's left is divisible by 26. And similarly in base 26, you can add up the digits and see if what's left is multiple of 25. Casting out 9s, casting out b minus 1. And then so on for 5 as well. You can do that in this. So then there's similar things that go on for other numbers. Like I figured out some pretty rules, like in binary, that you want to compute if it's a multiple of 2, you just see if it ends with a 0. Pretty simple. Just like in 10, if it ends with 0, it's a multiple of 10. And then for 3 and 5 and 7 and these other prime numbers and going up and in these Mersenne primes and stuff, this digit summation congruence is a pretty quick way to check for the membership of small primes pretty characteristically. Now I'm thinking of some applications for it. It's pretty cool. Because when you look at a prime, you look at a number and you use the fundamental theorem of algebra, you can take a number and say, well, I have a catalog of attributes. And I'm going to like to use this number as a multiset. So I'd like to know if this set contains these objects by whether 2 is the most common attribute and 3 and following these prime numbers are the descending in order later attributes. And so what I'll do is when I want to add it to the set, I'll just multiply the number by the set. So every set starts as 1 as the empty set. And then you just multiply stuff by it to set that attribute as being present on the set. And then if you wanted to compute, well, how many times does it have this attribute 2? Yeah, well, you just keep dividing until it comes out that there are none left. So this is a simple way to implement a multiset or an abstract data structure of computer science in a number. is called an algebraization, or it's called an arithmetization. An arithmetization is when you take something that's got an object model and you equate it to a set of numbers and operations in the numbers, and then you're able to just treat it like that number and act on it as by these numbers. An arithmetization. Okay. A geometrization is about the same. You just assign it to a thing to the geometry, and then you treat it like geometry. It's the same. And then, so these are useful things sometimes. Well, anyways, that's about what I was going to talk about today. Just something about analysis and methods, and that there's so many things that go on, and just getting one standard model of things, one standard curriculum, that there's so many other things that are just left behind all the time. And it's not then to say that we don't have more to do about it, but the idea is to figure out how to help bring those things together, and to make the curriculum kind of just have these attachments and detachments for it. This is all about this deconstructionist account, this deconstructivist narrative, and the reconstructivist, because to get it back together is quite a thing. Now, this other thing I have is it's a book by Emery Lakatos. It's from Cambridge University Press, Proofs and Reputations of Logic and Mathematical Discovery. And it's sort of a popular book, but it gets into a bunch of things that go into our developments of like the continuum and this and that. And it talks about the Dirichlet problem, which I'm looking into in terms of the Poincaré sphere and the Poincaré. Poincaré is said to be one of the greater mathematicians. So, looking back on arithmetic, and that it can be figured out a little variously, and then about the roots and powers, and then behavior of effective infinites. Again, these are things that are not standard, and they're meant more to encourage some kind of intuition and instinct about them, that otherwise that it remains how they're formally that they have arithmetizations, that they have geometrizations, that they attain to it, they have models, that they have limits, and they have these kinds of things. They have their closures. There's spaces of functions in them, in relation. There's operators about them, and calculus are the operators that make it so that what they have is guaranteed and well behaved, and this and that. And then a brief look at something about after the use of a model of a part of the theory of complex numbers above the space of real numbers. Well, because arithmetic by now has already got all of real numbers, so anything else we're just going to build above that instead of trying to deconstruct it or limit what we're going on with. And by the way, then it'll also work great for geometry and this and that, and the way things go. That then into the number theory, the integers in number theory. So we got analysis and methods, number theory, and analysis, or real analysis, the dynamical methods, anything that's in dynamical modeling. That's where everything ends up being dynamical modeling. So with models of things that are models of things that are models of things, then we can make it dynamical in terms of arithmetizations and algebraizations and geometrizations and standard and non-standard, about these various applications and the differential with the submersions and the sheaves and the symmetries as examples, about closed forms and perfect solutions, about approximations and their strengths and weaknesses and relative merits, getting things sensible, fungible, and tractable. It's all one mathematics. All right. Hey, have a great day.